Thank you, Ruslan. Welcome, everyone, to my keynote, Building Evolutionary Architectures. This is about a problem that we've had in software for a long time about how do we build software that ages gracefully and we can make changes to over time. This is the subject of a book I wrote several years ago with Rebecca Parsons and Pat Qua. And in fact, we've been asked to build a second edition of this book, which we're going to start working on soon. And the subject of this book is what I'm going to be talking about today. So when you look at the structural design part of software, you have requirements of some kind. And we don't really care how you got these requirements, whether it was domain-driven design or formal requirements gathering. You have requirements, but you also have a lot of other considerations, things like performance, and scalability, and data, and legality, and elasticity. These two things together, the requirements, the domain, and the architecture characteristics make up the structural design in architecture. And we focus mostly on these architecture characteristics. And part of what makes this complicated is that there are a lot of these things you can support in an architecture. Here's a partial list from Wikipedia of all the things you can support in an architecture. These are known as the ilities of software architecture because so many of them end in the suffix ility. What we're trying to do in this book and in this talk is add yet another one to this list, this idea of evolvability. But what does it really mean to have an evolvable piece of software? Well, let's say that you've chosen performance as a really important characteristic in your architecture. Having an evolvable architecture means that when you change something in your system, it shouldn't negatively affect performance. In other words, you've created a guardrail or governance around important architecture characteristics that allow you to change things in your software without breaking other important things accidentally. So I mentioned the word change. Change is interesting for us because we normally think of change as just one thing. But for us in the software world, it's really two different things because there's technology-driven change, and then there's also business-driven change. Technology-driven change are things like merging with a new company or new requirements because you've moved into a new market. Technology-driven change, though, is about these architecture requirements that I'm talking about. How do you protect those things over time? We've done a pretty good job at the business side, the domain side, with agile software engineering practices. But what I'm going to focus on today is the technology side of things, because the problem is we live in a very dynamic ecosystem. So if you look at the software development ecosystem, which is the combination of all the tools and frameworks and best practices and all the approaches that we have about building software up until very recently, that's what we call the software development ecosystem. And it's in a dynamic equilibrium, meaning all the pieces fit together, but it's also constantly changing. Because new capabilities keep showing up. The cloud is a great example of that. Another great example of that is when Docker showed up in our ecosystem a few years ago. Even if you're not using Docker yet, as soon as it appeared in our ecosystem, it made fundamental changes to the way that we think about our software. And this is a big problem in the software architecture world because everything changes all the time in our world. And this is a real problem for some roles in software architecture because how is long-term planning possible when things constantly change in unexpected ways? But why are we trying to predict the future in software? Well, change is expensive and difficult. So if we can figure out a way to plan around that change, then we can mitigate that cost. But what if you built your software with the assumption in mind that the ecosystem is going to continue to change at least the rate that it's changing now, and maybe even speed up some? How do you build protections for all of these things so that you can, in fact, adapt your software over time? If you can build change into your software, you don't need a better and better crystal ball. You can just adapt over time. That's what we're talking about here, are these guide rails that we place around these architecture characteristics for governing these features of our architecture. And that's an interesting word to use, because when we started out in this book, we were really focused on this idea of evolutionary change in architecture. But we realized that many of the things that we're talking about heavily overlap with this idea of architectural governance, because protecting those things for the future also means protecting them for now. And that's really the topic of architectural governance. So there's a huge overlap in the mechanisms that we talk about for evolution and the mechanisms that allow you to automate architectural governance. And I'll show you some examples of that in just a bit. So here is our definition. An evolutionary architecture is one that supports guided incremental change across multiple dimensions. And I'll talk about this definition in three parts. The first part of which is guided. This comes from one of my co-authors, Dr. Rebecca Parsons, who's the CTO of ThoughtWorks, spent some time in the genetic computing world. And in the genetic computing world, you're designing genetic algorithms that produce a result and then mutate themselves and produce another result and mutate themselves. And there are a lot of well-known mutation techniques within that world. If you're trying to influence the way that your genetic algorithm mutates, you can use a mechanism in that world called a fitness function. A fitness function is an objective function used to summarize how close you are getting to what your aim is. So, for example, if you were trying to write a machine learning program to try to determine something like the traveling salesperson problem. This is a well-known problem in computer science. You have a salesperson and they need to travel to a number of cities. What's the shortest possible route between those cities? So if I were designing a genetic algorithm for that, my fitness function would evaluate length of route and try to maximize, or rather minimize, the length of the route, because that's the thing I'm trying to get the best possible value for. And so we borrowed this idea of an evolutionary computing fitness function to create what we call an architectural fitness function. An architectural fitness function, just like an evolutionary computing one, is an objective function that gives you an integrity assessment of some architectural characteristic or combination of architectural characteristics within your ecosystem. Just like unit tests help you test the domain part of your design, fitness functions allow you to test the architecture characteristics or non-functional requirements part of your design. Because we've got a variety of mechanisms that help us manage the evolution of our domain, our requirements, unit tests, functional tests, user acceptance tests. Fitness functions serve a similar purpose, but for these non-functional requirements or architecture characteristics. Now, for unit testing, you can download a single unit testing library, but there are a lot of different architectural characteristics you may want to verify. And so there are a lot of different tools that allow you to do that. And I'll show you lots of examples of this as we go along. One of the things that we did in the book to illustrate these concepts was to create this fake company called Penultimate Widgets that encapsulated many of the problems that we saw out in the world. And one of the problems that I encountered out in the world is I met with some of our clients who were in the process of replatforming their core architecture. And when I arrived, they had come up with 66 goals for their next architecture. And I remember that number so well because I had a spreadsheet with 66 rows on it. And I asked them, hey, it's really good that you've identified all the things you want in the next version of your architecture. But if I come back in 6 months, how many of these things are still going to be true? And more importantly, how easily can you tell me how many of these things are true? Instead of putting them in a spreadsheet, if they'd identified those things as fitness functions instead, they have not only the verification mechanism, but the definition all in one place. So a fitness function in many ways is an objective way to state an architectural principle of some kind. And I'll show you lots of examples of those in just a second, but I want to finish my definition first. The second part of this definition talks about incremental change. And there are two aspects of this that are interesting for us. One is, how do you put new things live in an architecture without breaking existing things? And I'll actually show you an example of that at the very end of my talk today. The other part of incremental change is, once you've identified these fitness functions, how do you make sure they get run or executed on a regular basis? And the way you do that is with continuous integration or deployment pipelines or engineering techniques like that. And the third part of our definition talks about multiple dimensions. And this is really just the pragmatic awareness that when you talk about modern software systems, you can't just talk about the software structure. You certainly need to think about things like scalability and elasticity and performance, et cetera. But you also have to think about things like relational database design. In fact, we have an entire chapter in our book about evolutionary database design, because you can't just evolve the software without evolving the other things that are coupled to the software. Even things like security that some organizations treat separately, you still have to think about that, because it may influence some of your design when you're designing an architecture. So there's our definition. An evolutionary architecture is one that supports guided incremental change across multiple dimensions. Let's talk a little bit more deeply about this idea of guided change and this idea of architectural fitness functions. As I mentioned before, normally when I give the definition for this, I add the word any mechanism in there because unlike a unit testing library, for example, there are lots of different things that can serve as fitness functions. You can use code level metrics if you're looking at internal code quality or modularity or coupling between components, for example. You can use unit testing libraries. I'll show you a few of those that are specially designed for this in just a moment. For operational architecture characteristics like performance or scalability or elasticity, you can use things like monitors and other tools in the DevOps space. Notice that chaos engineering, even though they don't call what they're doing a fitness function, that's exactly what it is. Chaos engineering, of course, was pioneered by Netflix as a way of doing resiliency testing and availability testing for the Amazon cloud they were running on. That's the definition of a fitness function. It's an objective integrity assessment of availability, reliability, et cetera. And in fact, there are lots of new tools. Our book came out in 2017, and we've been encouraged by how many tools have come out to support this idea of automating architectural governance and evolution. So let me give you a concrete example. This is probably still a little abstract now. Let me give you a concrete example of a simple fitness function. And it's one that's applicable in just about every ecosystem that does something with components. Just about everything is component-based these days. And one of the things you want to try to avoid in component-based systems are cyclic dependencies between the components. That's where one component talks to another one, which talks to a third one, which talks back to the original one. This is bad because you can't reuse a single one of these components anymore without dragging all of them with you. And of course, if you allow this to keep happening all over your code base, you're tying everything together more and more tightly coupled, which is not a good thing in most code bases. But this is one of those problems that the universe is actively fighting you about this, because as you're coding along in your favorite IDE and you reference some class that you've never referenced before, what does your IDE do for you? Pops up a dialog that says, do you want me to auto import that for you? And you swat that dialog away so fast you don't even see it anymore. It's like a sneeze reflex. The problem is every single developer on your project has developed that same reflex that as soon as you see that auto import dialog, you just swat it away by saying yes and continue on with your work. And 9 times out of 10, 97 times out of 100, that's a great convenience. But every once in a while, it's tangling up your code base in a subtle but very damaging way. How do you prevent this from happening as an architect? Because you can't look over every developer's shoulder all the time. The way you prevent this is to create a fitness function. This is using a very old metrics tool in the Java world called JDepend that knows the relationship of packages in Java. Wiring this fitness function into your continuous integration means that you never have to worry about component cycles again. You can still allow developers to use those tools that they like an IDE, without accidentally damaging something important within your code base. We've defined a lot of categories about fitness functions, about things like the scope. Atomic fitness functions just run against a single thing, like coupling, the one I just showed you as an example of an atomic fitness function. A holistic fitness function looks at several things together because a lot of times these architecture characteristics get tangled up with each other. For example, if I want to improve security, I'm probably going to have a negative impact on performance because I need to do more on-the-fly encryption, more indirection for secrets hiding. And so sometimes you want to run several fitness functions together to see how they interact with each other. Triggered fitness functions are ones that are triggered by an event, like someone running a test or a continuous integration kicking in, whereas continuous ones just run all the time. So a monitor, for example, if you're monitoring performance, just runs all the time within your ecosystem. We also have, we would prefer most of these to be automated as much as possible, but we can facilitate and accommodate manual fitness functions as well, either because an organization hasn't reached the level of engineering maturity to be able to automate some part of their governance, like exploratory testing, or maybe it's something that cannot be automated yet, like legal requirements or something like that. So we can handle both automated and manual fitness functions. We want them to always have an objective outcome because that's how you can tell if it's working or not. But it doesn't have to be a single static fixed value. So some of them are a single value, like a true false or a number, but some of them are dynamic based on current input. For example, when you look at scalability, which is normally the ability to handle a large number of concurrent users, you typically also look at performance. And as the number of users go up, it's okay for performance for each one of them to go down a little bit, but you don't want it to ever fall off of a cliff. And so your performance metric may be based on number of concurrent users because that will have an impact on performance. So it's still objective, it's just dynamic. And so that's the distinction there between dynamic versus static. We also have temporal fitness functions, which are time-based fitness functions that happen on a regular schedule basis, for example. We sometimes get asked, are there any domain-specific fitness functions? And this is a good time to reiterate something that I mentioned before, that this is really a new tool in our engineering toolbox because we've had for a long time mechanisms that allow us to verify our problem domain. Unit tests, functional tests, user acceptance tests. Fitness functions are there for architectural characteristics. And this is a good litmus test to help you decide, should this be a fitness function or should it be a unit or functional test? Does it require any domain knowledge? So, for example, elasticity as an architectural characteristic. That is the ability to handle a burst of new users all of a sudden. So several thousand new people showing up to a website, for example, all at the same time. Notice I can talk about elasticity purely in the abstract. It doesn't matter what kind of site I'm talking about. It could be an insurance site or streaming video or gaming. It doesn't really matter. Whereas something like a change of address requires domain knowledge that should be managed by a unit functional user acceptance test, whereas elasticity, being purely an architectural concern, would be managed by a fitness function. And so we're adding another tool in our toolbox here from an engineering standpoint. So let's look at some more examples of these. Similar to the cyclic dependency check I showed you before, you can also use tools like this to define the directionality of imports. So let's say you have a code base where it's okay for persistence in web to import util, but you never want a developer to accidentally import all of web into util. That messes up your namespace or package relationship. And so using a tool like JDepend or Independ in the .NET world, you can define how you want imports to look within your code base. And then this checks as you check in code to make sure that it adheres to those things correctly. Not to make you think that all of these are these very low-level code metric kind of fitness functions. They actually exist at all levels of architecture. So here's an example of one in the integration architecture space. This is a common problem in microservice ecosystems where you have independent teams that are highly decoupled, but they still need to share information with each other. So in this scenario, the team in red on the left is providing some bits of information to all three teams on the right. And my architectural concern here is because each of these teams is evolving aggressively, I want to make sure that a team doesn't evolve in a way that breaks one of their integration points. And a common practice is for this is called consumer-driven contracts. Using a tool like PACT, PACT. There's a great write-up about similar tools on Martin Fowler's website, that you can see as the link there on the bottom. These consumer-driven contracts, each of the consumers puts together a contract test, hands it to the team in red, and they make it part of their build and promise to keep those contracts green at all times. And so if the team in red changes and it doesn't break any of their contracts, then great. We didn't break any of our assumptions. If it does break one of those contracts, then this is a placeholder for conversation. Let's get these teams back together and reestablish those contracts so that we don't have to constantly check with each other to make sure that things are not broken in our code base. I mentioned before the idea of Chaos Monkey. This is a great innovation by Netflix, and it's a great example of using a fitness function. The Chaos Monkey was so successful that they eventually created the entire Simian army. The Chaos Monkey was just there to create general chaos, but then they specialized it with the Simian army, where the Chaos Gorilla knocked out an entire data center, and Chaos Kong in the background knocked out an entire availability zone. Latency is one of the big headaches on cloud resources, so they have a special monkey that just stresses latency. So having that monkey there means that at any point when you write a service, that high latency may hit your service. So you have to defensively code against that because you're always trying to code against these chaos monkeys that are running against your ecosystem. The doctor monkey checks the health of instances like CPU utilization, disk space. The janitor monkey, these last three actually are really important to us because they're perfect examples of fitness functions. The janitor monkey looks for services that no one's routing to anymore, but costing them money and disintegrates them out of the ecosystem. The conformity monkey is where Netflix architects can write governance rules. So let's say, for example, that you decided that every service should respond to RESTful verbs with some reasonable value. You could write that into the conformity monkey to make sure that every service responds in some way to every RESTful verb. The security monkey is another great example of this. This is making sure that developers haven't left debug ports on or other security vulnerabilities. But this is also a great example of the real utility of this idea of fitness functions. This is not an excuse for software architects to go to an ivory tower somewhere and figure out new ways to torture developers and make their lives miserable. Instead, it's a way to codify important but not urgent things. There was a great book that came out a few years ago called The Checklist Manifesto, and it's about professions like surgeons and airline pilots who use or are sometimes legally required to use checklists as part of their jobs. And it's not because they're forgetful. It's not because they don't know their job. It's because that when you do the same job over and over, it's easy for details to fall through the cracks because you remember doing it but maybe not the last time. And I am certainly subject to this. Back when, before we all had to spend all of our time at home, I used to travel a lot for work. I used to average more than 2 time zones a week. But every once in a while, I would end up in some city without some critical thing like socks. And it's like, but I remember packing socks. Yeah, 2 trips ago. And so I created a checklist. That's exactly what these fitness functions are. It's a checklist written by architects for developers to make sure that important design principles are not falling through the cracks because of schedule pressure or some other factor that can distract people from doing the right thing. And let me show you some deeper examples of this and this idea of how much this overlaps with the concept of automating architectural governance. There's a great class of tools that have arrived, like ArcUnit. ArcUnit is a specialized testing tool in the Java world for testing architectural characteristics. It was built on top of JUnit and uses several of the helpers from the JUnit world. And it comes predefined with a bunch of governance rules, including things like, if you look at the next to last test here, no classes should throw generic exceptions. One of the things that may have annoyed you as an architect are lazy developers who, rather than subclass exception and throw a named one so you know why the exception got generated, they just throw a generic one, leaving it up to whoever catches it to figure out why it got thrown. If that annoys you, then you can prevent that from ever happening again by just snapping in this already predefined governance rule. So ArcUnit comes with a number of rules predefined for common scenarios like that. You can also control things like naming conventions. So you can look at the structure of classes and interfaces and names and other characteristics and define rules for them. But here's where the power of a tool like ArcUnit really comes into the fore. Let's say that you've designed an architecture that does a layered architecture with a presentation layer, business layer, and data access layer. When you design this as an architect, there's a very good reason you design those layers. It's for separation of concerns. You want to make sure that changes in one layer don't accidentally ripple into changes and to force changes in other layers. So that's the purpose of this design. But when you hand this to a group of developers to implement, how can you make sure they're going to implement it correctly? Either because they don't understand how important this is, or maybe you're in an organization where it's better to ask forgiveness and permission. How can you make sure that your design actually gets implemented correctly? Here's how you make sure of that. Notice that the first test here in ArcUnit is written using these Hamcrest matchers that says no classes that reside in a package service should access classes that reside in a package controller. Many of you as architects have written almost this same sentence in a wiki somewhere or some SharePoint portal, and it was right once, read never by anybody else, because you wanted to establish this important architectural principle, but principles that aren't tests, that can't verify themselves, don't have teeth, and it's easy to ignore them. Codifying these things as executables with objective outcomes that fail if they are violated makes it so that you can't skip them. ArcUnit also allows you to define your own governance rules for whatever kind of characteristic in your code base you're trying to check. ArcUnit is, of course, just for Java, but if you're in the .NET ecosystem, there's NetArcTest, which is a similar tool written for .NET using the same kind of fluent matchers and the same kind of a governance and verification for the .NET ecosystem as for the Java ecosystem. So a big part of the Evolutionary Architecture book is about this idea of fitness functions for evolvability. But there was another big idea that we ended up coming up with for this book. Excuse me. And it's called the architecture quantum. One of the things that we wanted to try to determine in this book was are some styles of architecture more evolvable than others, and why? And we looked at a number of measures of that, and none of them were sufficient for various reasons. And so we ended up creating our own measure called an architecture quantum. This is very much inspired by domain-driven design, which of course was the inspiration for microservices. And in particular, this idea of a bounded context from domain-driven design. Bounded context this is, of course, the underlying philosophy of microservices, but it's a really useful way of thinking about reuse and coupling in architecture. And we wanted the architectural equivalent of a bounded context. And we thought about just calling it bounded context, but the problem with that, of course, is that term already exists and it has a very specific definition in the domain-driven design world. And what we're talking about is slightly different, but captures some of the same flavor. And so we ended up creating what we call an architecture quantum. This is, in essence, a bounded context expressed in architecture terms. So an architecture quantum is an independently deployable component with high functional cohesion and synchronous communication. So independently deployable means that it's independently deployable and works standalone within your architecture. A way to think about this quantum measure is it's the smallest scope of something that still runs and operates within your architecture. High functional cohesion suggests that all the things are highly cohesive within it. So it's not the entire system, it's a subpart of the entire system. And synchronous communication is really about how things couple to each other when you call them. And so there are really two kinds of coupling that this quantum thing measures: static coupling, which is how things are wired together, and dynamic coupling, which is how things call one another. And synchronous communication changes some architecture characteristics. This quantum thing is really useful for reasons I'll show you now, for a lot of different reasons. One is for looking at the scope of architecture characteristics and defining the scope. So one of the exercises that we do when my co-author and I teach a live class is do these architecture kata exercises. So I won't read all this to you. This is what this kata describes: is an electronics recycling company where if you have an old electronics device like a phone or music player, you can go to a website or a kiosk in a shopping mall and tell it the model and the condition, and they will give you a quote. If you like that quote, they'll send you a box. You send it to them. They assess the device, send you money, and either recycle it or get rid of it or resell it and generate a bunch of reports. So if you wanted to look at this from an architectural standpoint, you can see three different clusters of capabilities here. The public-facing part of this, customer-facing, the assessment part of this, and of course, the recycling, reporting, and accounting. The customer-facing has one set of architecture characteristics: scalability, availability, agility, et cetera. Whereas the assessment needs fast change. I need to be able to change the number of devices on a regular basis. But recycling and accounting has money in it, so it needs security, et cetera. So notice that each of these has their own clustering of architecture characteristics, which means that as you build an architecture for this, those actually help you define where the scope of things should reside in this architecture. It shouldn't be a single system. It should, in fact, be three different systems, each loosely coupled to the other, because they each have different levels of security, different levels of scalability, et cetera. Now, you can't have asynchronous communication between these quanta, but that's what the synchronous communication part is about. Each of these forms its own scope of architecture characteristics. And this quantum thing is a really useful measure for things like microservices. So what makes microservices so evolvable, which we determined it is the most evolvable of these architecture styles? Extremely loose coupling, so you try to avoid things like transactions and do eventual consistency, restricted adherence to this idea of bounded context, and very small architecture quanta. And so that's why in microservices, you never see this API layer used as a mediator or something like an enterprise service bus, because all interesting behavior is supposed to appear in a bounded context within that architecture. excuse me, and you don't want to accidentally break a bounded context and put business logic in something like a mediator. So how do you put these things into practice, the mechanics of evolutionary architecture? Well, first, you have to identify what the important characteristics of your architecture are, the things that you really want to protect as things evolve over time. And this is really just an exercise of figuring out what are the really important architecture characteristics in my ecosystem. Then you define fitness functions, one or more for each of those dimensions. These are like guardrails that you put in place for those characteristics as they change over time. And then once you define fitness functions, use deployment pipelines and or continuous fitness functions to implement these behaviors to make sure that as you make changes to your code base, that all of these verifications are in place as you do so. And while a lot of this happens up front, this is an ongoing process within your architecture. You want to keep doing this over and over to make sure that you verify things as your system evolves. Just like unit tests, you keep your unit tests up to date always. As things change, you do the exact same thing for fitness functions. So let's go back and revisit the incremental part of this for just a moment. And I talked about the use of tools like deployment pipelines as a way to verify fitness functions. This also allows you to do things like a much larger global scope for things like fitness functions. So here's a great question for you. What does your organization do right now if you have a zero-day exploit for one of the frameworks or libraries you're using for development? This is not an abstract question. This happened to a major financial services company in the US in 2017, where a zero-day exploit came out for a version of struts they were using. So what did they do? Their security people ran around the company looking for applications using that version of struts, and they found most of them. Most of them. The ones they didn't find led to legal liabilities and a bunch of other bad things to happen. Imagine a world for just a moment where every single project is running a deployment pipeline, and your security team has a slot in every team's deployment pipeline. And when that zero-day exploit comes out, they can push a test into that deployment pipeline that says, wake up this deployment pipeline, check the version of this tool, and if you're using this affected version, fail your build and notify security. This allows you to automate architectural governance, including not letting important things fall through the cracks. So I'm going to wrap up today by describing this idea of incremental change, first in the abstract and then a tool that helps you do it. So let's say that you're running a website that has star ratings that run as a service, and one day you release a better version of star ratings. You don't force anyone to use it. It's just now a new capability in your architecture. And over time, services that need star ratings will evolve over to this new one until eventually no one's pointing to the old star rating service anymore. One of the tricks Netflix taught us about architectures like this is you monitor the services and the routes. And when you find a service that no one's routing to anymore, you disintegrate it out of your architecture. And in fact, we've already seen the mechanism that does that. That's the janitor monkey from Netflix's Chaos, the Simian Army crowd that does that, because you don't want that running and soaking up money if it's not giving you value. So here's the last example I'll show you from the GitHub engineering blog. A lot of developers think that adapting these really aggressive agile engineering practices like continuous deployment increase risk. But it turns out that you find ways to mitigate that risk. And this is a great example. GitHub, as an engineering organization, is very aggressive. They do continuous deployment. They average 60 deploys a day. They also operate at really high scale. And this describes a problem that they had about merge. It turns out since day one at GitHub, the way they have merged two files is to shell out to a shell script, tell command line Git to merge them, and then suck it back into GitHub. And that works great because command line Git knows how to merge things. The problem is it doesn't scale particularly well. And so they needed to fix this to write their own in-memory merge, which they did. And they did some testing on it, but now here comes the scariest part of my whole talk. Now they have to put it live. But here's the problem. You can't break merge on GitHub. It's never had a bug logged against it. So how can you safely make this surgical change without affecting other parts of your architecture? The way they did this and open source it so you can take advantage of it is this tool called Scientist. Scientist allows you to conduct experiments. Each experiment block has two clauses, use and try. Use is the old code you're in the process of replacing, and try is the brand new code you're trying out. So every time it hits this experiment block, it always executes use, and that's what it returns to the user, so you never get a surprise. But it also is configurable for how often it also executes try. And for the merge experiment, for 1% of cases, they also execute a try. When that happens, it randomizes the order in which try and run are used, measures the duration of everything, compares the results, swallows and records any exceptions, and then publishes all this to a dashboard. So here's right after the deploy. You can see that they are doing a little over 2,000 merges in the minute at 220. If you look really carefully at the bottom, you can see some tiny red tick marks. So let's zoom in on the bottom for the same time scale. Here are errors in their new code, but it hasn't affected their users yet because this is all happening behind the scenes. So they fix it and redeploy and fix it and redeploy. They were also looking at performance. And so here's the dashboard for performance, where the green line is the new code, so it's clearly better. They ran this experiment for 4 days until they had 24 hours with no mismatches or slow cases. Over the course of that 4 days, they did more than 10 million comparisons between use and try. So they had really high confidence that it was doing exactly what they wanted when they removed that code from the code base. That's a great example because all Scientist really is a fitness function that allows you to verify that the thing you're replacing is in fact replacing it correctly. So a few guidelines here. Most fitness functions are local. You want them to be really global, but they have to be applicable. So we don't want to create architecture police states here and create things that are not applicable. So keeping them local is important. And it's also critically important that teams collaborate. We don't want to create architecture police states here. So that's also critically important. They need to understand why these things exist. We prefer automation, but nothing is wrong with having manual. And so you can work your way toward automation. We believe that the definition of architecture is changing. We still have pictures, but I think more and more we can define architecture by fitness functions and governance, which changes the way we think about prioritization, and it also changes the way we think about things like cost. So there is a companion website at evolutionaryarchitecture.com that lists many of the tools that I talked about and has some other resources on it. Thank you very much for having me. And I hope you have a fantastic remainder of the conference, and I'm happy to answer a couple of questions.
Neal, thank you very much, Neal. It was a pleasure. And Rob, if you don't mind, we are going to Q&A session, and I wanted to invite Dmitry Dzuba to ask some questions to your person, if you don't mind. Dmitry, welcome.
Absolutely.
Thank you. Hello, Neal. Thank you for very interesting presentation, and we have several questions. The first one: what is the fundamental difference between fitness function and traditional quality gateway in development process?
So a great question. A traditional gateway in a development process could, in fact, be a fitness function. Just because you don't call it one doesn't mean it's not one. And so anything that has objective definition that helps you verify the integrity of something in architecture is, by our definition, a fitness function, whether the people who created it call it that or not. So the really important thing here is to not set up, for example, a performance monitor, but set a threshold on it so that an alarm goes off if it goes outside that threshold. That's what converts it from being just a performance monitor with a dashboard into a fitness function, which is why I stress this idea of objective outcomes. That's what turns traditional tools into actual fitness functions.
Oh, okay, thank you. And the next question, can you give an advice for those who want to adopt principles of evolution architecture in their organization? Where to start?
Absolutely. So the good thing about this is you don't have to eat the entire elephant. You can start very, very slowly. In fact, many teams are already doing this. They just don't call it that. So if you have, for example, Sonar wired into your continuous build, looking at code level metrics, that's a fitness function because you're verifying internal code quality. If you have a performance monitor that raises an alarm if it falls outside of a particular range, you are using a fitness function. And the nice thing about this is, and the way we recommend people do this is, the first one you implement is find something in your architecture that's causing you some problems. Maybe it's reliability or availability or latency, and build a fitness function around that. And once that's in place and working, find the next thing that's annoying you. And you'll eventually reach a point where, okay, none of these things are annoying me anymore, and you can stop. So this is not a framework that it's not an all or nothing thing. You can start very slowly, and we really emphasize the point that you want to do this only while it keeps adding value to your process, because we realize that this is a little bit of a sharp knife that we're giving architects, that architects could go overboard with this and actually create more trouble than benefit. And so it's important for architects to make sure they understand why this is there and not go overboard. And an easy way to do that is to start small and keep it small and always focus on value.
Okay, thank you. And I have a question. Can fitness function be used to determine the effectiveness of architects in company or whole architecture process? We all worry about it.
Well, if I could do that, then I wouldn't be writing a book about evolutionary architecture. I'd be writing a book about measuring developer effectiveness. No, and that's not something that's measurable. So one of the tricky things about fitness functions is you have to get it down to things that are objectively measurable. Those are the things you can write fitness functions for. And in fact, a lot of those process kinds of things would fall outside of fitness functions as well. That would be more of an agile development maturity model, for example, would be more probably more aligned with the question you asked about developer effectiveness. Developer productivity and effectiveness has always been elusive and continues to be.
Okay, thank you.